Today we're going to be looking at gas laws and how gases behave in relationship to their pressure, their volume, and their temperature. So we're going to be looking at three different gas laws, and the first thing you need to ask yourself is, what is a law? And so really that helps you explain a body of observation. So for example, if you look at Newton's first law of motion, if you're looking at something sitting on a table, it's going to sit there unless something comes along and moves it. And so you look at things that are sitting on a table and they're sitting there unless another force comes along and acts on them. And so we come up with a law of motion, and that is objects remain at rest unless acted upon by an outside force. So that helps us explain what we're seeing or our observations. At the time they're created, there's no exceptions to the law. So we're going to look at three gas laws today, and this helps us to explain what we're observing with different gases. So the first law we're going to look at is Boyle's law, and Boyle's law is used to explain the relationship between pressure and volume. And we have those three different variables that we talked about at the beginning of this vodcast with pressure, volume, and temperature. So Boyle's law looks at just pressure and volume. So Boyle's law says that when temperature is constant, that means it's going to be the same. Volume decreases, pressure will increase. So you can also go the other way. If volume increases, then pressure will decrease. And so what we have here, when one goes up, the other goes down. And this is called an inverse relationship. So let's say I have this weird looking balloon here that's a Mr. Maxwell face, and I can control the pressure in this chamber, and I have air particles inside this balloon. And so if I decrease the pressure, if you look over here, then if I decrease the pressure, then the volume will increase. And so what we're seeing here is if you decrease the pressure, the volume is allowed to increase because those particles can now push and expand, and that increases the volume because there's less pressure. So what would happen would be the balloon would expand and you'd have an even creepier looking balloon. So those particles are allowed to press out because there's less pressure, and so those particles can press out on the outside of the balloon. If you did the opposite, and again you start with a regular sized balloon, and this time we're going to increase the pressure, then the volume would go down in that balloon. So what would happen is the pressure would increase and those particles would be pressed together, so you'd have a decrease in volume. So it looks something like this. So now you'd have a decreased volume because of your increased pressure. Now our balloon would be crushed into a much smaller space. Charles's law, this is not a typo. This is actually how Charles's law should be written. His last name was Charles, so this is Charles's law. But it's used to explain the relationship between volume and temperature when pressure is constant. So if the pressure is constant and there's a change in temperature, there should be a change in volume. Now this is different from Boyle's law in that Boyle's law was an inverse relationship, but Charles' law is a direct relationship, meaning when one goes up, the other goes up, or when one goes down, the other goes down. So with Charles's law, you have that pressure is constant and temperature increases and volume also increases. And the easiest way to think about this is a hot air balloon. When you add heat into the hot air balloon increases in volume. So here our creepy balloon is back. There we have our strange Mr. Maxwell face balloon again. And with Charles's law, we're going to increase temperature or decrease temperature, and volume will respond in the same way. And again, if you remember what temperature is, it is the average speed of the particles. So if we increase the temperature, the particles are going to move faster, and they're going to push on the container at a greater force, and that's going to expand the volume. If it's not in a closed container, as temperature increases, those particles also move faster and spread apart too. So if we increase our temperature here, then again I increase the volume of the strange looking balloon. Now if I want to decrease my temperature here, then what do you think would happen to the balloon? So if we decrease temperature, then we should see a decrease in volume. So that would make a much smaller balloon, depending on how low you decrease the temperature. So when we're decreasing that energy or increasing that energy, we're going to see an increase or decrease in volume, depending on if we're increasing or decreasing the energy. I won't spend too much time here on Gay-Lussac's law, but it's kind of the next logical step with these three variables of pressure, temperature, and volume. And what we're looking at here is that Gay-Lussac's law is used to explain the relationship between temperature and pressure when volume is constant. So the best way to think about this is like an aerosol bottle. So with Gay-Lussac's law, think of it like an aerosol bottle that is being heated. And if you heat an aerosol bottle, I think most of you know at this point in your life that if you heat an aerosol bottle, the particles inside are going to move faster. So we got faster moving particles on the inside, and if they're moving faster, then they're going to be hitting the inside of the container more often. And so what that does is that builds up pressure on the container. And eventually, if you heat it up too much, you'll know if you throw an aerosol bottle into a fire, it will explode. And so that's obviously not something you want to do. Now this works the opposite way also. If temperature decreases, then the pressure will decrease. And again, because temperature is a measurement of the average speed of the particles, that would make sense because they're moving slower, and so they're hitting the inside of that container less frequently, and so the pressure on that container is going to drop. And so again, this is a direct relationship, just like Charles' law was a direct relationship. So here's your homework for this podcast. After watching this and going through the three different laws, I want you to look at these 8 situations and tell me which law applies to each situation. And you need to write that down on a sheet of paper and bring that to class for our next class period.